So, welcome to the Zimbabwe podcast today. I'm joined by Mr. Jason Shingirai Makechemu,
Yep.
and he's the current president of the Zimbabwean Astronomical Society, or ZAS, or ZAS, and a final year PhD student in astrophysics at Lancaster University. So, Jason, I really appreciate you for joining me today, like we said earlier.
Yes, thank you too. I appreciate it. I'm happy to be here.
Yes, very excited.
Mm.
But I just want to start really simple. Like I said prior, I might have to do a lot of catching up to understand a lot of things. But just to start off simple, when you study astrophysics, what do people actually think you do? Because when you tell people, "Oh, I study astrophysics," we can think, "Oh, he just looks at the stars," or he just looks at the sky, right? But
Yeah,
what do they normally assume that you do when that's the first thing you say?
that's a good question because it depends where I am. It depends where I am. Usually, let's say when I'm in England, people are like, "Oh, that's nice," or "Oh, you're too clever for me." Like they don't really say
Right.
much about astronomy. I think most people in the UK kind of have like a vague idea, like we look at things in the sky. That's pretty much what most
Yes.
people are who aren't educated on the field. Like some people
Mhm.
say, "Oh, like, do you think we can get to Mars?" And I do a lot of extracurricular reading, but that's not what I do.
Yes.
Astrophysics is relating to the stars. So not just any heavenly body, but stars and what's are composed of stars, like galaxies. But when
Mhm.
I'm in Zimbabwe, people are just absolutely confused. You have to tell them what a star is, why we look at them, why is it useful, how do we even do that? And they'll be like, "Oh, so are you going to go to space?" It's a foreign topic for most people. Like in the capital city, it's more people kind of know, but there's a lot of people also in the capital who kind of have no idea. So it's just about saying it on the most surface level possible.
I could see a lot of people just kind of being like, "Oh, you're an astronaut," or something, right?
Exactly. People are like, "Oh, so you're going to Mars?" But it's interesting because my parents initially, because they're very educated. Like my parents are quite educated, so they're not like typical in the African sense of be a doctor and that's it. But
Right.
even then, when I was talking to them about astronomy, they were confused. They're like, "So what's the point? What's the benefit? Well, you have a job, which is fine. They just have a good
Yes.
concern for you." But have you heard
Mhm.
of Neil deGrasse Tyson?
Yes. Yeah, absolutely.
And Neil deGrasse Tyson was probably my biggest inspiration. And when I was a kid, I didn't know it was something that you could just do. I thought these people were like, I don't know, they had special connections or something. I didn't know
Right.
anyone could study astrophysics. So it was a big inspiration, but it wasn't until maybe the year before I started my undergrad when I realized it was something I could actually study. So yeah.
That's really cool. Yeah, Neil deGrasse Tyson, love him. I mean, the Star Talk
Yep.
podcast, yes, so entertaining. He did it
Dark
so
Knight.
well. Just yeah,
Yeah,
communicating science, he aced it.
yeah,
Aced it.
for sure.
Well, yeah, that's awesome. And so, with all of that, what do you actually spend most of your time doing as a PhD in astrophysics?
That's a good question. Um, I think most people give the same answer to me, which is reading and coding. Because,
Cool.
these days it's less about going and actually operating the telescope and, physically by hand. Actually, on my first year of undergrad, I think in the first 2 months, I went to the Canary Islands. It belongs to Spain off the coast of Morocco.
Yeah.
Um, and I was there operating a telescope, putting in the inputs of where the telescope is going to look, collecting test images and all these things. But I didn't realize that I was actually part of the last few astronomers to actually use it physically because then it was made robotic. So most telescopes now are robotic. You put in information, they collect the data by themselves. And then
Right.
once you have the data, pretty much from there it's programming. You're trying to get the raw image and make it look presentable. You're trying to get specific outputs from the image. You're trying to run some data analysis and all these type of things, which 99% of the time is just programming. And the reading part comes in terms of what are we going to use this data for and what have people done before, or even just trying to
Mhm.
understand what we're looking at. So, um, yeah, those are pretty much the two main things. Um, we go to conferences sometimes, present our work, listen to other people's work. I've been to quite a few. But as a PhD student, you, I think it's one of the few areas where you're pretty much already doing the thing. Like this,
Right.
yeah, you're already like thrown in the deep end, to be honest. Yeah.
I know that's interesting. And I heard you say coding at the start, which kind of caught my or raised my eyebrow. That I was like, coding, really?
Yeah, yeah.
Is that something you can expect nowadays, like you said, because everything's becoming automated? If
Mhm.
you're looking to become a PhD in astrophysics, should you expect to begin coding or learn coding?
100%. I
Wow.
was even just thinking through, is there anything we don't use coding for? Because, I talk to a lot of people in different areas of astrophysics, like
Mhm.
stellar astrophysics, where you try and understand how, like, the mechanisms of stars, or galactic astrophysics, understanding how the galaxy works, or extragalactic astrophysics, where you understand different types of galaxies. And you always need to have some coding skills, some more than others. Like for me, due to the nature of what I'm actually working on in my PhD, is more technical than what most people would do. But
Mhm.
to some degree, you need to. But the good thing with coding also is that it's very, what is it called? Coding is a transferable skill,
Yeah.
If you if you're in your undergrad or master's degree, you don't necessarily have to have done astrophysics. As long as you do some practical use of coding that could be transferable to what your PhD will be in, then it's all good. Yeah.
Absolutely. Wow. Because
Yeah.
I always assumed, I mean, looking from the outside in and watching movies and
Yeah.
seeing videos, I assumed astrophysicists just have a giant chalkboard and put
Yeah.
a bunch of physics equations on there, and you guys are just looking around. But of
Yeah.
course, I assume it's more data visualization now and sorting and all of that kind of stuff.
Some people still do that. Have you watched Interstellar?
Yes, I have
Yeah.
a poster. It's behind my curtain right there.
I think it's one of my favorite movies,
Yes,
Interstellar.
absolutely.
And it made me think of like the chalkboard scene. That's what theoretical astrophysicists would do. I'll give you an example. So
Okay.
let's say I'm trying to understand how um our galaxy rotates, like, because
Mhm.
in astrophysics, the general rule of thumb is everything rotates. So the Earth spins on its own axis, right? That's
Mhm.
what makes a day. Like if you have this bottle, it rotates like that. Then the Earth rotates around the sun. So this is the sun. The Earth is going also around the sun. And also our solar system, which is the planets near us, Mars, Earth, Jupiter, and the sun, are going around the center of the galaxy.
Mhm.
And the galaxy itself, with everything included in it, is also rotating. And there's physical mechanisms behind that. There's actually a lot of complexity in how that rotation happens and all these types of things. So a theoretical astrophysicist would tell us how it's happening. He would make his calculations and say, okay, the galaxy is rotating because of this and this and this. But us observing, we'll just look in the night sky, observe its rotation, and we'll check. So if the theoretical astrophysicist does his calculations and says, okay, the galaxy should be rotating at this speed, and
Mhm.
we go and check and it's a different speed, he has to go and revise his calculations. Or if it's the same as what if we observe the same thing he predicted, then all is good. So the theoretical
Mm.
astrophysics is kind of like doing the groundwork, explaining what we see. Yeah.
Right. Oh, okay, that makes a lot more sense. So a
Yes.
theoretical astrophysicist essentially, I don't know, writes a blueprint maybe,
Of
and
how
then an
things should work.
observational, yes, should work, how they
Yeah.
should work.
Because a lot of the time things don't work as you expect in the assumption, so to speak. You calculate things, you're like, huh, that's weird, and that's how every major discovery happens. It's
Yeah.
someone calculating something, and we see something different, and things are revised in that way. It's yeah,
Mhm.
iterative.
It's very interesting. Has there been a theoretical astrophysicist who's just been the complete best, has gotten most of everything right?
Einstein. you know,
In like yeah.
I tell people Einstein is synonymous with genius, right? But
Mhm.
even at that level, I really think Einstein is underrated because so one of his biggest contributions are special relativity and general relativity.
Mhm.
So the general idea of these two theories is what are the properties of space and time? So have you heard of something called time dilation? Maybe I should explain time dilation.
Oh, I believe so. Is it
Yeah.
actually, no, fill me in, please.
Yes.
Yes.
So time dilation, time was assumed to be static, by the way. Wherever you
Mhm.
are, no matter what you're doing, time is fixed. It's a immutable property of the universe. So Einstein comes along, he says, I wonder if this is actually true. So long story short, with all his complicated derivations, I have not even done 1% of of the information that he's shown us.
Mhm.
time is not immutable. Time and space are uniquely linked. So let's say you're traveling at the speed of light, right? The faster you go, the less time you experience. So a photon, which is the particle of light, if it travels at the speed of light, it experiences no time. And if you're traveling half the speed of light, you experience more time than the photon moving at the speed of light. But you experience less time than a particle at zero motion. So one of the key findings of special relativity is that time is not immutable, it's not something fixed that never changes. It depends on what's happening around it. And gravity also affects time, and Interstellar, we had this huge planet. It was gigantic. The gravity of it was so huge, and the gravity is actually impacting how time is working in that area. So that's general and special relativity in a nutshell. And he also worked on something called the photoelectric effect, which is when you have light hitting a certain object, let's say made of metal, and then you'd have other particles offshooting as a result. And even Brownian motion, which is how does a large amount of particles in a given area move? Like how do you calculate the air moving in this room? Or in a stadium? You use Brownian motion, so statistical mechanics to understand such things. So yeah, that's Einstein. That's most of his work.
Yes, and I always see videos of it's kind of insane that he was able to work everything out at that time, and everything just keeps getting checked, and it's like, yes, you're right. It's
Yeah.
absolutely insane. Yes, his genius is definitely overlooked, even though we all call him the genius already.
That's why he's a genius.
Yes.
Even Isaac Newton,
Mhm.
Newtonian dynamics, gravity, even he, in his framework, you could actually, if I remember correctly, also time dilation. No, gravitational lensing. So gravitational lensing is when you have a massive object, let's say the sun, and light is passing behind the sun. Because of the huge gravity of the sun, the light is bending. It's bending in the gravitational path that the sun creates. His calculations were off because there was no relativity involved. But there's a lot of creative things you can do generally. With Newtonian dynamics and physics.
Oh, yes. And I always wonder, is there a prominent figure modern times that has a standout, obviously not to the levels of Einstein, but standing out above the rest in theoretical physics or just any practice of physics study?
Well, there's a man named Adam Rees. I hope I have his first name correct. Let me just yes, Adam Rees.
Yes, sorry.
Yeah.
Adam Rees.
Adam Rees, yes. So he was part of a team that in the 90s proved and shown and proved that the universe not only is expanding, but the expansion of the universe is getting quicker. That was a huge result, because it transformed the way we view the universe. It was already shown that the universe was expanding. That's Edwin Hubble. And then not only is it expanding, but it's expanding even quicker than it was, a year ago, 10 years ago, a million years ago. So he is quite prominent. There are quite a few. The thing is, I'm not tapped into the famous names, A lot of them. Oh, actually, there's a Andrea. I'm not sure how to pronounce her last name. And Andrea Ghez, Ghez. She's an American theoretical astrophysicist. She also won the Nobel Prize a few years ago for they say it in a very jargony way, but essentially for showing that the supermassive black hole at the center of our galaxy, that actually exists. They use observations over a few years, maybe I think a few decades, showing that we have different objects orbiting at the center of the universe, and the only thing that could explain the motions of these different objects was a supermassive black hole. So yeah, there are quite a few people who made very, very famous discoveries. Jocelyn Bell Burnell, I don't know if you've heard of her. Jocelyn Burnell. She's actually at Oxford. I met her one time.
Oh wow.
she she discovered pulsars when she was a PhD student. I think she was a PhD student. Yeah, she discovered pulsars. It's a bit controversial because the Nobel Prize went to her advisors instead of her,
Mm,
taking credit type of situation. But she
all right.
nowadays she's very well regarded as the person who actually found such things. So
That's
we
good.
still have quite a lot of people, and it's not just them. We have a lot of people who are very prominent in astrophysics these days. So yeah.
That's very cool. Very,
Yeah.
I enjoy seeing. I think it's happened more as I've gotten a little older. I'm not too old. I'm only 24, but
We're the
as
same.
I've like gone through my teen years, you're 24 as well. You said,
Yeah.
"Oh, look at us! Look at us!"
Yeah.
But
Mm.
I've seen science communication just explode. I mean, with the likes of Neil deGrasse Tyson, Brian Cox. I'm
Yeah.
sure you've heard of him as well. It just came onto my feed, and before that, prior to that, I wasn't big into wanting to know, but I feel like a lot of people in this current generation are wanting to know, wanting to learn more.
Uh-huh.
It's great to see that. And I've seen that you put, like if you checked your website and your resume, like you are a science communicator, and I love that. It's
Yeah,
amazing.
yeah. I did it for a few years when I was when I was an undergrad at a
Hmm.
university called Aberystwyth University. It's on the Welsh coast in the west coast of the UK in Wales. Wales is a separate country.
Hmm.
um, So yeah, I was an undergraduate there. I had a good time. I gave some talks. And a lot of what I did was online. Like I made TikTok videos, you know, talking about
Hmm.
different things in astronomy. Even when I started my PhD for the first year, I was making YouTube videos. Um, but work got in the way of such things.
It
A
gets
lot of
busy.
science
Yeah.
communicators you see. Have you heard of Dr. Becky?
Dr. Becky, I'd have to see maybe a
She's
photo.
she's a one of these other big voices in popularizing science, and she has a very
Hmm.
sweet spot in the sense of making it accessible, but also providing technical details. I really like her channel. Um,
Yes.
sorry, it was just work that got in the way. A lot of these people, they don't actually do like currently the science full time because
Right.
communication is a huge job in itself, producing videos, editing, traveling, collaborating. It's a lot of effort. So, and I also don't think I'd want to be a communicator full time. I really like the science. So that's
Yes.
another thing. Yeah.
Yeah. It's a lot harder than people think. I would think to
Yeah.
make even YouTube videos just
Mhm.
on any topic.
Oh,
It's a lot
yeah.
of work.
That's true.
But I wanted to circle back to when we were talking about relativity.
Mm.
Could you explain more of the famous like twin sister paradox? Because I know that's kind of what we were referring to in the traveling of different times relative to each other.
Yeah. So I can explain to some level. There's a lot of paradoxes actually. Um, So this is regarding time travel. Like, would you be able to travel through time? Let's say you have two sisters on Earth, two
Hmm.
brothers, whoever, two people on
Hmm.
Earth. One of them goes on a journey and they travel, let's say 50% the speed of light, which is still ridiculously fast. Like 50% seems like not much. I don't even think there's any technology, even hypothetically, that could get us to travel that fast. So it's very hypothetical. Let's say she
Hmm.
traveled 50% the speed of light on one journey, and then she traveled 50% of the speed of light on the way back. Her sister on Earth ages normally, like us, It's not like she's traveling at light speeds or even fraction of light speeds. But because her sister's traveling, time is slowing down for the one who's going and coming back. So when she comes back to Earth, her sister would have aged at a normal rate. But because she's traveling so fast and time is moving slowly for her, she would be younger than her twin sister. Yeah. It's not
It's
something that really makes conceptual sense. And I no, there's a few YouTube channels that explain such things quite well, and they'll go through the calculations. I remember when I'd be working out things for time dilation for things like that. I'm like, huh, this is very weird. But these things are actually testable. These things aren't just hypotheticals. So, there were two atomic clocks, the most accurate time measurement instruments that we have. And I think there was one on the top of the mountain, of a mountain, or in the International Space Station, something like that, where there's lower gravity than at sea level,
Mhm.
or the effect of gravity is less. And the two clocks differed in time, ever so slightly, but they differed. Why would they differ? Because of time dilation due to the effects.
Yes, and I saw a clip of Dr. Michelle Fowler.
Yeah, I know her.
Have you ever heard of?
Yeah.
Yeah, and she was speaking about that,
Mhm.
specifically that atomic clock thing. I think she said one of them was in the International Space Station
Yeah, that's what I
for
remember.
whatever.
Yeah.
Yeah, but she also said technically, like let's say your upper body, your head,
Yeah.
is at a different time than your feet, and I was like, what does that even mean?
Yeah, technically, if I don't even know if you
On
could
this
measure
the
that.
small, yeah.
It'll be the smallest time measurement you could possibly have, but yeah, because there's a slight difference in experience versus, I don't know, 1.7 meters or however tall you are,
Right, right.
Yeah.
But yeah, that's a lot of the science that I hear. Obviously in clips, it's going to push the most fascinating ideas and everything, but it's I can't grasp, essentially grasp it or understand it in
It's
my
not
little
it's not
human
it's
brain, I
not
guess.
intuitive. It's not intuitive at all.
Mhm.
And that's what I find fascinating about science. The most polarizing ideas are the ones that kind of are not intuitive to us at the time. So yeah, a lot of people don't understand a lot of these theories, which is why it's so controversial. And one thing I see when it comes to talking about the Big Bang, for example, is how can something come from nothing? That's a big question. I don't think anyone has the answer to that, unless you're religious.
Mhm.
The Big Bang actually doesn't talk about how things came into existence. It talks about what happened at the earliest point of the universe's existence. It doesn't talk about how it came into existence. So a lot of people don't understand, like, these scientists think they know everything. Nah, 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 nah. No, we don't think we know everything, but there's some things we can investigate. And a lot of us are very cautious when it comes to saying types of things, certain types of things. The I remember, like, right now I'm trying to publish a paper that I worked on during my PhD. It takes so much effort to get a paper out. People are checking it. They're triple checking your questions, your answers, your methodology, and everything. I'm like, okay, yes, people get things wrong, but when something's been rigorously tested for 80, 100 years, the chances of that are less. You know?
Mhm.
Yeah.
For sure.
Mm.
And that's a good point to bring up because I know you mentioned before our conversation that you specifically wanted to discuss faith as a scientist.
Yeah.
And science and faith, and honestly, like you said, are often presented publicly as opposites.
Yes. Yes.
Most people say you have to pick one,
Mhm.
essentially, right? So, what does that relationship actually look like for you personally?
Yeah, I wanted to talk about it because it's something that when I was a kid, everything is presented as opposing. Um, I don't know if you watch a lot of maybe not a lot, but if you've heard of these new atheist people like Richard Dawkins, Christopher Hitchens, a lot of them argue from a naturalist perspective, right? That if you are a rational person who understands science, you cannot accept anything that is opposing. So these new atheist people would rely on a lot of scientific arguments like, oh, evolution, oh, Big Bang, etc., etc. People don't realize the Big Bang idea was postulated by a Catholic priest. Very verifiable. If you check who first came up with the idea of the Big Bang, he was a Catholic priest. I don't know his first name, but it was Lemaitre. Not to say that that means they should be automatically trusted, but not everything is in opposition. And for
Right.
me,
Yep.
I wasn't always religious. I'm an Orthodox Christian. I was baptized in the Ethiopian Orthodox Church, actually the oldest church we believe that exists. And I didn't always believe in God, but I went for this internship at Oxford University,
Mhm.
and I was very surprised because a lot of it was a group of us from around the country, and there was this girl who was also from America, who was coming to us from America, and I was surprised that people there believing in God. I was like, oh, there was this Scottish girl. She was a Church of Scotland. There's this Irish guy. He's Catholic. There's this Ethiopian girl. She's Ethiopian Orthodox. So I was like, wow, maybe there's some validity to, people who believe in God and um, believe like are scientists. So that's when I started exploring. And, I kind of had in my head that atheism wasn't really a very defensible position for various different reasons, you know? Like, it was hard for me to defend, I should say. And when I would see
Mhm.
people arguing about it, I couldn't really understand their defenses either. So I was like, okay, there has to be something. So, you know, there was Islam, there was Judaism, there was Buddhism, Hinduism, Christianity. And, you know, I did a lot of investigation. And, you know, there's very little conflict. People try and present it as conflict because it comes from the idea that religion is a man-made story, you know? Or they don't necessarily know how things are interpreted. You know, when you look at Genesis, for example, you know, like there's some Christians who think that the earth is 6,000 years old, you know, like literally. So when you ask them about dinosaurs and ancient civilizations and all these things, it sounds a bit crazy. You know, there's a lot of
Mhm.
chaos on both ends. There's atheists who have good arguments and don't agree with Christians. There's Muslims who have all sorts of
Right.
arguments. But for me, I really don't think that there's a conflict between let me say specifically Christianity and science, you know? And I think even science would agree that there are things that we'll probably never be able to understand, even from a scientific perspective, you know?
Yes.
Like,
Yep.
yeah, and I think that just because something may never be understood doesn't mean it's necessarily false. I think it's more of a new age thing where people think that the two have to be opposed, but that's not necessarily the case. Yeah.
Yeah. I think it's very like you said, everyone just it has to be opposed.
Yeah.
But I hope that changes and people can just hope, you know, you can keep your ideas and you can keep yours. It doesn't have to be we have to butt heads. I have to prove
Yeah.
you wrong necessarily.
Yeah. And if you look at it,
Yes.
actually, it seems more like a cultural thing, you know, like for example,
Mhm.
um, in Ethiopia, you know, I've been to Ethiopia many times. There's this actually famous Ethiopian astronomer. His name's Dr. Rodas. Um, I think he's a deacon in the church, and he's also a very prominent. He's like the Neil deGrasse Tyson of Ethiopia, you know.
Ah,
So,
yeah.
you know, there's huge voices from both ends of Christianity and science, and you can have a very uh, normal relationship between the two. You know, they're not mutually
Yes.
exclusive. You know. Yeah.
Mhm. I mean, you're probably correct about a cultural thing because I'm in the United States
Yeah.
and I see the polarization of
Yeah.
you're right or you're wrong.
Mm,
And I wouldn't have expected, like you said,
mm,
when you met your colleagues that were also religious
mhm,
and studying astrophysics or science.
mm.
That's just not what I would have expected at all. I thought
Yeah.
it was one or the other. So yeah.
Yeah. I was surprised.
Mhm.
Mhm.
So and I know you spoke about it a little bit, but how specifically did starting to study, I guess, the universe just as a whole, how did it strengthen your faith or challenge it or changed it in
Oh,
kind of a way? Yeah.
that's a good question. Because even me, you know, I was kind of like a science only person. I was like, there's no need for God. You know, we have evolution, we have the Big Bang, we understand how things are made. But when you actually look at the technicalities and intricacies of things, it makes you believe in God more. You know, even me, when I think about something coming from nothing, you know, that for me, that is not a that doesn't really test my faith. It's more something that strengthens it, you know, because these are things that, according to all known current laws, or ancient laws and future laws of physics, it should be impossible, you know? I don't think there's anything scientific that's really tested my faith since I've been a Christian or even since I've been looking into it. Um,
Mhm.
because you know, I accept a lot of things, you know, I accept the Big Bang and I accept so many aspects of science. I'm an astrophysicist, you know? I can't be denying science and good at my job at the same time, but you can believe in God and then you can also be good at your job at the same time. So yeah, I think for me it was just seeing the fact that there were other Christians who were scientists too, which kind of like planted the seed in my head. The thing is, for me, when I was looking into Christianity, I was confused. I didn't grow up as a Christian, right?
Mhm.
So it's kind of like science. You know, just because a scientist says something doesn't mean it's true. You know what I mean? So just because a Christian says something doesn't mean it's true. So initially, I was looking at different churches. You know, Church of England, Catholic, Eastern Orthodox, and I guess I had doubt when I was looking at each of these things because each of them, from my perspective and from my reading of history, had things wrong with them. So when I'd hear, like in the Church of England, for example, you know, some of the things they teach about, you know, Jesus or salvation or science and all these things, I was like, nah, this is not for me. And I was in a state of limbo, you know, I was in a state of limbo
Right.
for maybe 6 months because, you know, I'd learned about the Catholics. I'm like, mm-mm. So, you know, I think it kind of discouraged me from that church, but not from God, if that makes sense. Because,
Hmm.
I didn't think God was exclusive to these different institutions. But when I found the Oriental Orthodox Church, which the Ethiopian Orthodox Church is a part of, I mean, it sealed the deal for me. Every doubt I had was cleared. All the questions were answerable and everything. And I have to give a lot of credit to my teachers. I had a lot of good teachers, encouraged. you know, they kind of knew the mindset I was coming from, so they encouraged a lot of questions and criticism and all these type of things,
Hmm.
which is good. So after I found that, it was peaceful. I don't have any doubts. Yeah,
Yeah.
yeah.
Well, and speaking on like your early path,
Mm.
like when did space and just the fascination of everything go from something you enjoyed
Mm.
to, oh, I could make this a career and I could pursue this? I know you spoke a little bit about Neil deGrasse
Yeah,
Tyson being an inspiration, but
yeah.
what was that moment where you're like, I'm actually going to do this?
Yeah, I mean, the thing is, when I was young, even in my mid-teens, I just liked science. Astronomy
Hmm.
wasn't like particularly ahead of everything else. I loved biology too. I was interested in engineering to a degree, robotics. When I was a kid, I was very good at maths and science. So I knew, like, pretty much, I knew I was going to do something in the STEM field, right?
Hmm.
So I think the thing is that kind of like sealed the deal is when it comes to popular science communication, astronomers do the most. So when I'd be watching documentaries on YouTube, um, like you said, Brian Cox, Neil deGrasse Tyson. I watch different podcasts, like Star Talk, documentaries on. I don't know if you know what the BBC is, like BBC News,
Hmm.
like yeah.
Yeah.
So I'd watch documentaries there, and there's this documentary, Fermat's Last Theorem. It's not actually astrophysics related. It was a mathematician who's still alive who solved one of the most complicated um, maths problems ever. And me just seeing people doing amazing things like that led me to know I wanted to do science. But I think it was just before I started my degree, actually, when I was like, okay, I'll do astrophysics. Um, because I was deciding between, I think, it was biomedical engineering and astrophysics. So I remember I had a phone call with my dad. He was like, okay, why would you do biomedical physics? I was like, fair enough, because I didn't know anything about it. And I was like, okay, I'll do astronomy. Initially, though, I started space science and robotics. Um, my parents, with good intentions, they really wanted me to do engineering. So when I got to university, that day I switched my course to astrophysics. I wanted it to be pure astrophysics. So yeah, I mean, it wasn't really a very detailed path. I just knew I was going to do something sciencey, and it kind of fell in my lap.
Okay. Yeah, I'm sure. And I'm not sure of the exactly of the process,
Mm,
but I know at least for my degree, it was just simple, an information systems degree. So I
okay.
guess IT and business, you
Yeah.
could say. But during in that period of my undergrad, you kind of have 2 years to
Uh,
do your prerequisites, and then you could pick.
mhm.
Was that the same for you? Was like you can just run through all your science, and then you could be like, okay, I actually want to do this? Or were you like first day while you're doing your prerequisites that I'm gonna do this the whole way?
Okay, the thing is, in England, our degrees are 3 years. So
Okay.
uh, technically even less than 3 years because you graduate in 3 months before it would actually have been 3 years. So it's more like 2 years and 9 months. So when you pick your degree, 99% of the time, that's what you're doing. I kind of was lucky that both degrees were in the same department. So they're like, okay, go ahead. So there's no prerequisites or anything like that. Once you start your degree,
Oh,
that's it. So that's why a lot of people, you have to do career guidance and all these things, or talk to your parents and all this stuff to make sure that what you're doing is appropriate for you based on your grades before and all these things.
yeah, that's probably that's probably better. I mean, we have a big culture here of switching kind of halfway or at the end, and then it adds up into a lot of money. I think you
Yeah.
could imagine, but
Hmm.
yeah,
Yeah.
that's interesting. But I mean, going back to the start again,
Mhm.
growing up,
Mm.
I mean, I probably have some of the kind of the same experiences you in that sense of my parents told me, you know,
Mhm.
it's really what you want to make money,
Mhm.
to have a career, to have a sustainable life,
Yeah.
all of that. So did growing up, I guess you didn't know until the end, but did
Mm.
becoming an astrophysicist feel realistic for you?
Well, well, kind of making money. My dad is self-employed. You know, in the beginning,
Mhm,
like he did web design, he does social media marketing and all these different types of things. So
mhm,
he kind of very much instilled in us business, 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 you know, try and make money. But,
mhm.
you know, I don't know if this is your experience, but it's funny, you know, like when people, like my parents came to England in just before I was born, you know, better life and all these things.
Yep.
You end up having a better life and making different choices, which is something I don't
Yes,
think a lot of
yes.
immigrants' parents understand, you know? So for me, I was like, I wasn't all about the money because I had a good upbringing, you know? I'd be playing tennis, I'd be swimming and all these different, I was chill. So for me, I was like, okay, money for me growing up wasn't that big of a concern. I don't want to pick something I enjoy. So I knew I wasn't going to do business. I was kind of funneled into doing engineering. I even went to an engineering school, finished, but I didn't like it. So it wasn't about it feeling realistic. It was just something I didn't even think I could do. You know what I mean? It's like kind of, I don't know, imagine watching like a Tom Cruise documentary. It's not like people think, oh, I'm going to be Tom Cruise, you know?
Right.
It's
I
just like,
understood, yeah.
it's like, wow, you know, it's just being amazed at what's there.
Yes, it's really amazing. Was there ever a moment when you looked at data or something, or when you went on that trip? I watched your YouTube
Yeah.
video of that, by the way.
Yeah.
You taking your naps and stuff, I remember.
Yeah.
But was there ever a moment you felt like, "Wow, I'm actually studying the universe, like,
Yeah.
this is my wow moment?"
Okay. I do have a wow moment, but it wasn't that trip because
Mhm.
I didn't like it. High altitude, so I was sick. And then I couldn't sleep properly because you'd have to wake up early to go to the telescope. But at the same time, you had to stay up very, very late into early hours of the morning when it's best time to observe. I don't even remember most of the trip. I was deprived of sleep and energy. So that wasn't the trip. I would say maybe when, mm, that's a good question. I think when I had the first results from my paper that I started working on when I was in Oxford. Because, you know, I was working, because, you know, Oxford, I don't know about in America, maybe for you it's Harvard and MIT, but for us it's kind of like a legendary institution. You
Yeah,
know, it's a
it's legendary over here
yeah,
too, we understand.
you know, thousand
Oxford,
year
yeah.
old institution, and these people are the
Yeah.
best at what they do. So I was like, wow. And then I was like working on
Yes.
research with them. I couldn't believe it. So at that time, and when I had the results from my paper, I couldn't believe it. That for me, that was the wow moment. Or maybe even because the year before I went to Paris, at the Institute of Theoretical Physics at Paris-Saclay University. That was also very cool, but I think it was my first introduction to astrophysics. Um, I was supervised by a lady called Natalie Hogg. Now she's at Cambridge. So that was very cool. But I think Oxford was more surreal to me, you know? Yeah,
Yes, I mean, Oxford, like I said over here, is still regarded as one of the most legendary institutions, of
yeah,
course, along with Harvard, like how we view Harvard
yeah.
and everything like
Mhm.
that. But yeah, speaking of being with such intelligent people
Mhm.
and going to Oxford, which is amazing,
Yeah.
congrats to you on that for the internship. But was there ever a sense of imposter syndrome? I know it's a very big thing, and
Yeah.
I mean, every career
Mm.
is imposter syndrome, but I couldn't imagine being surrounded by
Yeah.
people at Oxford. How was that feeling?
It was actually quite okay. Because you know, my parents instilled a sense of whatever you're going to do, do it very well. You know, so I
Mhm.
didn't really have much time to think about, oh, am I good enough, etc., etc. The thing that made me kind of self-conscious wasn't when I went to Oxford. So the UK system is weird. Usually you do an undergraduate degree, you do a master's degree, then you do a PhD. So I applied for master's degrees and I got offers, but I didn't get offers for funding. And
Mm.
degrees are very expensive, like £15,000 a year, like maybe $20,000, you know? Very
Yeah.
expensive. And you can take out a loan, but the loan doesn't even cover the tuition, so I wouldn't have food to eat.
Right.
So I started applying for PhDs. I was like, I don't have a master's degree, so let me try. And I got 3 offers. So I was like, okay. But when I started, I was kind of like, oh my goodness, I don't have a master's degree. There's a lot of things that I don't have, like in terms of experience. It ended up being okay, but it was a worry of mine in the first year or so of my degree. So yeah, of my
Yeah.
PhD.
Wow.
Sorry. So yeah.
Right. Did you ever seriously consider quitting or stopping or switching, for that matter?
Um, I think is I couldn't because I was already in too deep. Like,
Yeah.
and it would look so bad, you know?
Yeah.
You drop out of your PhD and what are you gonna do, you know? Yeah, I didn't think about it because I knew it wasn't a possibility, you know?
Mhm. So what's next after the PhD? I don't know what the next steps are after.
Yeah, that's a good question. So I've always wanted to live and work in Africa.
Hmm.
So the thing is, I was born and raised in the UK, but I'd often go to Zimbabwe for visits. And I started,
Mhm.
visiting Africa more so in the last 2 years or so. So next step, hopefully, God willing, I'd say, I would work in Africa at some point. And I'm not very fussy. Yeah, that's the next step. I think I've already explored job opportunities there, so we'll have to see. Yeah,
Awesome.
yeah,
And you're the current president of the Zimbabwean
yeah,
Astronomical Society,
mm,
correct? And
yeah,
what is what does that look like? What does that mean for you? Because I'm sure you, like you said, you visit back a lot.
yeah, yeah. Um, there are a lot of responsibilities, coming from abroad, Europe, England especially. There's a lot of
Mhm.
expectations people have, and a lot of questions, intrigue, and things like that. Africa is really overlooked when it comes to a lot of progress and scientifically, not just astronomy, but in general. And there are a lot
Mhm.
of well-educated people, old and young, who have a lot of curiosity, expertise, skills that can be utilized, and it's the same everywhere. It's not like a complaint, but that's just how things are. You can't. Not
Right.
everyone pays attention to everywhere, and it's inspiring to see a lot of work being done. Actually, um, there's the current vice president Tobe Kile Ngwane. um, she's actually doing a lot of the work right now because I'm doing my PhD. Like, I'm almost done with my PhD. I'm working on my thesis and everything. So she's actually doing a lot of the work, and a lot of people are responsive. We're actually due to have a hackathon soon in
Oh,
October. So that's going to be very cool with the help of the African Astronomical Society funding and International Astronomical Union Office for Astronomy Development. So
that's very
we're gonna
exciting.
host that at our space agency, at the Zimbabwe National Geospatial and Space Agency. So that's very cool. We're trying to make a lot of connections with the University of Zimbabwe, our National University of Science and Technology, our space agency, different groups, working together, which is a good thing.
Mhm. That's really, yeah, that's amazing that you have that such big events lined up
Yeah.
too.
Mhm.
And so what is the landscape of, I guess, astronomy in all of Zimbabwe look like right now?
So in Zimbabwe, we have a Professor Nyambuya. His first name is Golden. His full name is Golden Gadzirai Nyambuya. And if I remember correctly, he's the first Zimbabwean PhD holder in astronomy, at least the first homegrown one.
Wow.
Um, he's still quite young, in his 40s or 50s. I don't want to overestimate his age. So he's at the National University of Science and Technology in the south of Zimbabwe. And he mentored a lot of students who actually now are helping with the society. Like I mentioned, Tobe Kile. There's a
Mhm.
guy called Praise, and a lot of people who worked with him who are now doing astronomy by themselves. He's a theoretical physicist by trade, but he mentors a lot of students in different ways. So that's the landscape pretty much. Our space agency doesn't really work on astronomy. There's an unofficial department of astronomy, but mostly it's Earth observations, satellites. Um, yeah, from what I understand, that's mostly what's happening. Yeah,
That's cool. So he's kind of been a mentor for
yeah,
like putting the grassroots down to
mhm.
bring astronomy to Zimbabwe.
Exactly. And that's the only university that actually has a, a functioning astronomy department. There used to be astronomy at the University of Zimbabwe, but there's a lot of issues with astronomy happening there, so it's not really taught, but people are trying to revitalize it. Yeah.
Is astronomy, and I mean, I guess just the study of science, well accepted in Zimbabwe? Is it a faith-based country, or how does that look?
Yeah, it's fine, and in Africa, people there's less of this like science and God conflict, like even when
Mhm.
I tell people, my family, both of my grandparents' sides and my cousins, my uncles, they're quite religious, but it's more like what are you going to do afterwards? Because, you know, a lot of Africa is not a country where people can just do science freely and there's research institutions and things. You don't really have that. So it's about like, how are you going to feed your family, you know? So most people do
Mhm.
farming, mining, real estate, things that are more practical. Um, but in the educational sector, you know, if you go to the universities, if you go to the research institutions, they'll be like, oh, yeah, this is a good thing to do, of course. But just in the general public, people just think it's a waste of time. Yeah.
I mean, I could see that. It's a different
Mm.
lifestyle. I mean,
Yeah.
like you said earlier, your parents went to England for like a
Mm.
chances at a better life, and then they set you up in a way that you didn't have to
Yeah.
think of becoming a miner to support your family. You
Exactly.
had the lifestyle and the choices.
Yeah.
That's good. And I mean, so what do you hope to be accomplishing as a president?
Mm. That's a good question. If I'm being very honest, I am actually going to hand off my presidency soon. You know, it's because I don't think I have the enough time and
Hmm.
involvement on the ground to be a good enough president. But in terms of being involved with the Zimbabwe Astronomy Society, I just hope you see a revitalization, revitalization, I think that's the right word, of astronomy in Zimbabwe. You know, I want our top universities to have the astronomy departments again, you know, for, you know, um, general awareness to be made, you know, communicating astronomy in our local languages, you know. We have a lot of the terminology. People don't know that we have a lot of the terminology actually there in our native languages, and it would be very good to have educational material in them. And just, you know, being more involved in actual continental scientific research, you know. You know, politics plays a big role in why Zimbabwe is not involved. You know, all our neighbor countries are involved: Zambia, Botswana, Mozambique, South Africa, so many countries. But you know, hopefully, you know, we'll come into an era where there's more continental astronomical research happening. You know, there's no reason why Zimbabwe can't be involved. You know?
But I hope it gets better
Yeah.
for a lot of things. But
Yeah.
what do you? I know you said you're going to hand off your role, but
Mm,
if a young person in Zimbabwe who loves space,
mm,
right? What do you want them to have access to, like that you did not when you
mm.
were first starting?
You know, I want them to be able to go to a school or a university and have someone to talk to or to help them with things, you know, just knowledge, even something as simple as a textbook, you know, where you can
Hmm.
see images of the night sky and some descriptions of what's being seen. Or if you go to university, there's an astronomy club, you know, like people have telescopes or binoculars. You know, we don't have grand vision, so to speak. You know, we want to start from the grassroots level, you know, of just
Hmm.
being able to access such information. You know, a lot of people, because I think a lot of people don't realize, even in Zimbabwe, still today, most people live in the village, in rural communities. So for them, they actually do have kind of a lot of knowledge of the night sky. You know, they actually do.
Yes.
You know, they can track seasons, weather patterns, um, obviously, there's some traditionalism involved. You know, there's a lot of traditions involved in rural communities. They have indigenous names for the planets and some of the constellations and things like that. They do have a lot of knowledge. So it's actually quite funny. More people in the city have less knowledge than the people in the village. So yeah,
Hmm.
we're trying to bridge the gap, you know, the knowledge gap, so to speak.
Yeah, I think that's very normal too
Hmm.
over here as well, or anywhere. If especially nowadays with all the light pollution.
Hmm. Right.
I mean, I live in a big city,
Mm.
Houston,
Wow.
Texas, right? But I grew up in a smaller city in I don't know if you Minnesota. It's way in the north,
Yeah,
so
I know Minnesota, the state, right?
yeah, right, yeah. And I lived in a small city there,
Mm.
not a lot of light pollution. So I grew up looking at the sky,
Mm.
and it was always a fascination. But I talked to my friends who I have down here, and it was never the same. They've never seen what I've seen, and I couldn't imagine what people see in more rural
Yeah.
areas.
It,
So I feel like the fascination's always there.
yeah, it's amazing. I've only witnessed such a sky one time. I mean, I've been to the village many times. Usually, I'm sleeping. There was a time when I looked up at the night sky. I was like, "Wow!" I was just like this the whole night. You know,
Yes,
it
it.
was amazing. You know, in England, you don't really see much. Even in Harare, the capital city of Zimbabwe, it's getting brighter. So it's also a
Mhm.
bit tricky to see such things in the night sky over there too. Yeah.
Yeah, a lot of people will never ever see what is truly up there, and
Mhm.
I think that's kind of sad because I think that's where most of the natural human fascination
Yeah.
of what is that? What is up there?
Exactly.
And I hope that brings a lot of more people in. But what do you think the biggest barrier for someone in Zimbabwe who wants to enter astronomy? Is it like funding? Is it accessibility? I mean, I guess those could be two in the same, but
Mhm.
what do you think?
For someone who's just looking into, trying to know more about it because of curiosity, it's accessibility, It's not a
Mm-hmm.
priority. And it's good, actually. It's good, in my opinion, that Zimbabwe is not focusing on astronomy right now. There are more important things to do. But there's always a way to balance things, If Zimbabwe allocates a budget of $1 million, for textbooks, that's not going to stop them doing anything else. It's a very rich country, So I think it's just striking the balance and having more
Mm-hmm.
educated people in government, um, and even local institutions. Because, there are a lot of people in universities who acknowledge the importance of access to information, you know? But yeah, it's bureaucracy and things like that, or low priority.
Right.
Yeah.
Of course.
Mm.
And that makes sense. But is there a lot of exposure to it naturally?
Uh,
Just or no, not so much.
no, not really. I think you could go your whole life without hearing about astronomy. I think
Oh, wow.
I think
Yeah.
you could, to be honest. I mean, even because a lot of people in Zimbabwe, like, we obviously have internet and social media and stuff, but
Mm,
for people to just be, browsing on YouTube and looking for those type of things, it's not very common. I know some people who have, but it's not common. Most people are either working in school, but a lot of people work very hard. Yeah.
yes, for sure. Of
Right.
course. And would you ever think about long term becoming faculty
Mm,
in Zimbabwe somehow and
mm.
kind of spreading that?
Long term, yes, but short term, no, because money.
Right.
Like, money is not my only priority. Otherwise, I'd be in industry. But
Yeah.
they don't pay very much. I mean, you could survive, but I'm used to European standards of living, and I wouldn't be able. It wouldn't be comfortable for me to be on like $400 a month, like it wouldn't
Yeah.
be. And also, setting up for the future, planning for the future, it wouldn't be a good idea. Maybe in the long term, because salaries used to be very good. $2,000 a month, $3,000 a month, which in Zimbabwe is very, very good. But
Hmm.
things changed in the educational sector, so not so much these days.
Oh,
Yeah,
I gotcha.
yeah,
And yeah, I mean, I guess it's a very long term
yeah,
goal naturally, even if you're in London or whatever. That's
mm,
after your
yeah,
career and studying, I
yeah.
suppose.
But
But
I
that
love
brings,
being in
yeah,
Zimbabwe. I really do like being in Zimbabwe. But
yeah.
just as a career, it's not the for a career like mine, it's not the best. If I was a farmer, yeah. If I was a miner, if I was like into mining, then yes. But not, or even,
Hmm.
yeah. I wouldn't. I wouldn't have an issue. But for this, yeah,
Yeah. Do you ever think about moving back permanently? I mean, not, I mean, I suppose you never live there, but you visit a lot.
yeah, yeah, yeah. I've thought
But would
about
you
it.
figure move permanently?
I
Yeah.
definitely would. It's a possibility for sure. Maybe once I've retired, or if there is a job with good prospects in the future. So yeah,
Yeah, things can happen. Things can
yeah,
happen
for
for
sure.
sure. Yeah, but that brings me to kind of what you're studying now.
Mm.
I wanted to touch base on when I've only gathered information from what you had on your website. I know that was kind of old, you said.
It kind of. I haven't updated it in like a year or two, so it depends.
Yeah.
Yeah.
I, just based on what I saw,
Yeah.
I saw like when you say you study galaxy dynamics,
Mhm.
right? I hope that's the correct
Yeah, yeah, yeah.
terminology,
That's
but
correct. Yeah.
what does that mean in normal language or like language that people like me could understand?
When it comes to galactic dynamics, as we put it, it's concerned. It's a study concerned with the movement of galaxies or what's inside them. So, for example, how a galaxy rotates is part of its dynamics. That's how it moves.
Hmm.
Also, inside the galaxy, if we're concerned with what the gas is doing inside or what certain things are happening with inside, that's also part of galactic dynamics. It's what's dynamic within or of the galaxy. Yeah.
Okay,
Yeah.
so so what is actually moving inside a galaxy then?
Okay. So a galaxy is huge, by the way,
Hmm.
incomprehensibly large. So Think of our solar system. We've got 8 planets and a sun. In a
Mhm.
typical galaxy, there's about 400 billion stars.
Yeah.
That is an average galaxy.
Mhm.
So a galaxy is huge, and there's a lot of stuff happening. So let's say, I'll give you an example of star formation. A simple picture of star formation is you have a huge cloud of gas and dust, very big, and it's pretty stable. Not much is happening. But then something happens to destabilize it, and the gas cloud collapses. Through that collapsing and the extremely high pressures generated within, a new star is formed. Right.
Mm.
So we have this huge ball of gas. We call it a molecular cloud, where there's different
Mhm.
molecules kind of in a huge cloud. Collapse and we have a star. And there'll be thousands of such molecular clouds within a galaxy. So that's one thing. But the dynamics of the galaxy, like how it rotates, could impact how those clouds end up forming stars.
Mm.
There's different types of rotation of the galaxy, or the speed of its rotation, or even if it's rotating differentially. I'll give you an example. When you have something rotating, it can rotate faster on the inside and faster on the outside, slower on the inside, for example, or vice versa. It's called differential rotation because everything's rotating at different speeds.
Mhm.
So due to something like that, it can affect how things happen within the galaxy. Sometimes it might make star formation better. Sometimes it could make it worse. It just depends on the situation. Yeah.
Okay. And what is better and what is worse?
Oh, okay. Better. Well, those are very loose terms. For star formation to be better, it's like more stars to be made. It's a
Okay.
better environment for stars to be made. And worse would be if there's no star formation happening. Yeah, in this context.
Hmm.
Yeah.
Interesting. Okay. And then what controls and you said the pressure
Yep.
when what controls that pressure?
Oh, there's a lot of things. So let me give an example. Let's say you have a cloud that's stable. No, nothing is affecting it. It's
Right.
pristine.
Mhm.
Let's say there's a supernova somewhere close by.
Mhm.
The star explodes, disturbs the cloud. Now the cloud is turbulent and unstable. So because of how massive it is,
Mhm.
it depends on the mass of the cloud. If it's so massive, because of the destabilizing pressure, it's gonna collapse. You know, so it's something along those lines where other things like a supernova or even a black hole coming close by or something else can destabilize the cloud and cause it to just be destabilized, be turbulent, collapse, all these different types of things, possibilities, I should say.
Hmm. That's interesting. And I, I don't know if this question makes sense so much though, but when we talk about all these supernovas or even this gas cloud or
Mm.
just things occurring in the universe or even in a galaxy or in distant galaxies, I understand that we have our own little solar system, but why is there never things happening right next to us? Or, it's always distant,
Yeah.
far in another galaxy or
Mm.
light years away in our own
Yes.
or something like that.
Okay.
Yeah.
It's a good question. Let me pose an example to you. Let's say you're in Texas. You just find a random spot in the desert. You drop
Hmm.
down. Things are happening everywhere. There's tsunamis, crashing into the oceans. There are
Hmm.
thunderstorms happening everywhere. Earthquakes and everything. But you're in this tiny, tiny little place in the desert. So it seems like nothing's happening, but it's because you're away from everything. You know what I mean? So
Hmm.
it's like the galaxies or the universe. We're in a tiny, tiny, tiny part of the galaxy. It's so minuscule. You know, I wish there was a visualization we could use, like to show you how small it is. But it's kind of like us, we just dropped in the ocean. We basically see nothing. It's kind of like that. And the spaces between objects are so huge. And even here's a cooler example. Let's say we lived in a violent place in the universe, right? Where there's supernova happening all the time.
Hmm.
There
Hmm.
probably wouldn't be life on Earth because these
Right.
supernova emit so much energy, Earth would be vaporized. So, you can look at it two ways. Maybe because we are not in a very chaotic environment, that's why we're actually here to witness things. or maybe if there's a chaotic environment, we would not be Like we wouldn't be able to even investigate these things, you know. So if there was supernova right near us, we would have been finished a long time ago. Yeah.
Yes.
Yeah.
And I know you said we kind of live in like this perfect
Yeah.
place for life.
Mhm.
Have we found any other systems that
Mhm.
have kind of been coded like us, a perfect system?
Well, that's why I don't actually like the term habitable zone, you know,
Mm-hmm.
because let's say, like we do now, right? We live in the perfect place from the sun where the sun's energy is just enough to keep the oceans watery, you know, they're not frozen like Mars. And also, you're not too far when they become icy or too close when they'll be evaporated, right? But that
Mm-hmm.
doesn't account for so many things. Because yes, we're in the habitable zone, but that's not enough. You know, the planet has to have water in the first place. Not every planet just has water. Um, there has to be no violent things happening near you, like no exploding stars, which is strip away the atmosphere. Um, we have to have a good atmosphere, you know, that insulates us from the sun's rays, you know, and keeps the temperature stable. All these different types of things. So, yes, we found planets in habitable zones, but a lot of them are gas planets, you know, like Jupiter, where there's no surface
Mm-hmm.
or there's too much radiation because the sun is different. You know, they have a different star as their sun. So many things that are complicated, and they might not even have the, you know, from an evolutionary perspective, the right ingredients for life to occur. You know, so there's a lot of things that are complicated when it comes to talking about a um, habitable zone. Yeah, you're in the habitable zone for temperature, but nothing else is habitable. So
You need many more. Yeah.
yeah,
And so I understand that beyond the habitable zone, you need so many more
yeah.
things
Mhm.
to create life. But how many habitable zones have we found? Just out of curiosity. Is it a lot or is it not so much?
So the way to phrase it is, how many planets have we found within the habitable zone of a star?
Mm,
Because let's say we remove Earth and Mars. There is still a habitable zone, but a planet has to be there.
right.
You know what I mean? So, I mean, I'm pretty sure dozens, on the order of dozens. Like we've seen many, many planets that are, you know, in the right place where water can be cool and the radiation will be too much, etc., etc. But that's kind of like step 0.5. You know, having a planet conducive for
Hmm.
life. So a lot of people, to be honest, if you're doing astrobiology, for example, where you're trying to
Hmm.
understand the conditions necessary for life extragalactically, that won't excite them too much. But it's part of the way there, you know.
Yeah, it is just, that makes sense. And honestly, this might, again, be way out of reach, but this popped in my head. When we talk about gravitational pull and that Earth sits on like this, from what I understand, like a net
Oh,
of,
okay. I see what
right?
you're
That,
saying. We're talking about curvature, right? Yeah.
yes. And
So
that's due to gravity, right?
yeah,
Correct?
that's true.
Okay.
So a visualization we use, you know, curvature of space and time. Bigger masses will result in more curvature. So think about like the sun, right? You'll have a deep well. Anything that is
Hmm.
close to the sun will fall within its gravitational well, so to speak. You know, it'll be more susceptible to the gravitational force that the sun has because of its mass. So yeah, every single object has such a thing. You know, the Earth does, the Moon does, even the tiniest stones have such a thing. You know, so yeah, that's the case, and that's why you'll have smaller objects tending to orbit the bigger one because of such a thing. Well, technically, they orbit the center of mass between the two objects, but usually it will look like the smaller object is orbiting the bigger one.
Hmm.
Yeah.
And what did they mean by I understand like the curvature of like the fabric of space. It's like
Mhm.
dropping a marble into a sheet or a blanket, right? It'll pull down. But what do they mean by the curvature of time? That I don't understand.
Yeah. So space and time are intertwined. You can't
Hmm.
really have one without the other from a pure physical perspective. Obviously, we do that all the time in colloquial speech, in human speech, but it's not something that can actually physically be separated. And time also behaves differently around massive objects. You know, the more gravity, the slower time is going to move because of that gravity. And the light will actually
Right.
bend around whatever object you're using, you know. Obviously, the bigger the mass, the more it's easy to tell the bending of light, you know, as it's going around the path, you know, it'll actually follow the path that the big object is how you say it? Like when the space is curving around the bigger object, the light will follow that path. So the bigger object, the easier it is to see. But yeah, because of that, it's yeah, I don't think you can really separate them meaningfully. You know, that's why we always say space time. Not we don't say you know, you can say space and time, but we say space time because you can't really separate them.
Interesting. That always confused me. And
Mm.
so, a planet further away from us, since they're further from the sun's gravitational pull, would have a different sense of time relative to us
Well, yeah,
because of the
yeah.
gravity.
Yes, because of the distance, but also because of the size of the planet. Yeah, but these
Mm,
things, I mean, the scale that they're happening are so like we wouldn't perceive it if we was, let's say hypothetically, we could stand on Jupiter. We wouldn't really sense it. You know, you have to
yeah.
really take it to the extremes. But yes, that would be the case.
hmm
Mm,
Interesting.
mm,
And then I guess we could go back to. I had a question here about kind of what you study,
mm.
and it was started here. How can a galaxy contain the gas needed to make stars, but still kind of basically?
So remember, I was talking to you about dynamics, right?
Mhm.
Um, let's say you have a galaxy. You know, it's got all the gas and dust it needs, but the gas is kept stable. You know, because remember I said for the for the molecular cloud to collapse, a disturbance needs to happen. You know,
Right.
there'll be any kind of disturbance, objects flying through it, a supernova, etc., etc. But if these molecular gas clouds are kept stable against gravity, you know, then you know against because gravity wants to bring it in, so the opposing force will keep it stable against the gravitational force trying to keep it in. If that is able to happen, then nothing's gonna happen. The stars aren't going to form. So yeah, I actually wrote it's in an advanced draft stage, a paper about this. Um,
Huh.
let me find the equation for you. Yes. So there's something called the epicyclic frequency, which is essentially the frequency that the disk is rotating, the gas is rotating in a disk. If it's very high, it's a stabilizing force against gravity. So if you have a very, very high frequency of rotation of the disk and that gas in the disk, then even though you have all the gas necessary, a star won't necessarily form because of the collapse of that cloud. The cloud will actually probably wouldn't even collapse. Yeah.
Hmm.
Yeah.
Okay, that's a,
Yes.
it's. I mean, I think I understand it to the best extent I can, but
Yeah. Yeah.
that's
Hope so.
awesome. Oh, thank you. But like, what what is your current research? The research that you've been doing, what is it trying to figure out that astronomers or scientists don't already understand? Like, what is your research leading to? Ideally, I suppose.
And that's a good question. I mean, so in astrophysics, there are many ways that we try and understand the history of the universe. And one of those ways is understanding star formation. So, how these stars form. And we have a pretty good idea of how stars formed in the early universe, in the middle, and now. And it pretty much follows
hmm
a curve like this. In the early universe, there wasn't that much. In the Middle Ages, so to speak, there was a lot of star formation, and now it's also decreasing. So my study is, are the ways we try and predict how this star formation happens accurate? And as a follow-up study, how can we improve the accuracy of such measurements? So I use radio telescopes. So telescopes observe the universe in different wavelengths of light. So visible light, you know, the light we see, you have a telescope that looks in the sky like that. Yeah,
hmm
X-ray light, ultraviolet, etc., etc., etc. So I use radio wavelengths, and radio wavelengths have an advantage because if you look at like a plot of like the length of the waves, radio waves are very long. They can be many meters long. So one wave is like very long. So they go through the atmosphere with pretty much no interference. You know, if you have lower wavelengths,
Yep.
they get interrupted by our atmosphere. So that's another key thing. And radio waves have been used um, for decades. You know, as calibration tools for star formation. So it's actually probably one of the best wavelengths to investigate in because if there's any issue, my discoveries are very consequential. And if there's also no issue, then it also means I've confirmed that what we've been using is good and acceptable. Yeah.
Mhm. Okay. And how do stars emit like radio waves? Is it the movement of the planet, or I mean the star,
Yeah.
or
That's a good question. So we're not necessarily looking for what's coming out of the star at that time. We're looking at the
Mhm.
universe, like the individual galaxy as a whole. Each galaxy will
Okay.
emit specific markers telling us that star formation is happening. You know, obviously, like if you just have a picture, like just a visual picture of the galaxy, it'll look, what color is it? It'll look blue. Yes, it'll look blue. If the galaxy is red, this means like star formation is pretty much finished. Um,
Hmm.
so there's similar ways looking at different wavelengths, in radio and X-ray and other wavelengths that can also tell us whether star formation is happening or not. And then you use more complicated diagnostics to tell how much star formation is happening. Yeah.
Hmm. And for a red, I assume it's like a dead galaxy
Yeah. Mhm.
or something. Can those galaxies begin creating stars again, or is it just forever obsolete?
That's a very good question. Yes, we use the term red and dead galaxies. Yeah. It's bleeding, so to speak. So yeah, pretty much most of the time, actually I'd say the vast majority of the time, they will not produce stars again. And if they do, it won't be suddenly like from a red to a blue galaxy again. It'll just be sporadic here and there in the galaxy. But it's pretty much done. Yeah.
Hmm.
Mhm.
And that brought me to another question. For a star specifically, I don't know if I remember this right from my 8th grade science class, but when a star dies, doesn't have a couple options depending on a lot of circumstances to become a dwarf, a giant, or just completely collapse, etc. I always wondered, when that change happens, is it gradual or is it like an instant? Like when it's ready to die. Let's say the sun, it's ready to go. Whatever it turns into, is it just a or is it like zzz type of thing?
It's a good question. So yes, you're right. Different stars will meet their demise in different ways. So smaller stars will tend to just end up expanding due to the lack of counterbalancing pressure. There's a lot of outward pressure.
Hmm.
So the sun, well, like let's say our sun is no longer fusing hydrogen. It'll end up expanding when it's run out of fuel. And it's not like it'll just expand in an instant. All these things happen gradually. And there's other ways stars die too. Like there's these binary star companions, which are what
Hmm.
lead to supernovae, What happens is the bigger star and is taking mass from the smaller star. So the biggest star is getting bigger and the smaller star is getting smaller. Eventually it reaches a limit called the Chandrasekhar limit. It was an Indian astrophysicist who actually coined this term. I think he won the Nobel Prize for that actually. But yeah, so there's something called the Chandrasekhar limit. And once the bigger star reaches its limit, it goes kaboom. And that one is pretty much instant. It releases so much energy. There's actually been recordings of supernova sightings from historical writings. And these stars are
Wow.
billions, I mean, trillions, quadrillions of miles away, So they're
Hmm.
extremely energetic explosions. And if one happened, you know, next to us, it wouldn't even have time to react, really.
Wow.
And also the likelihood of it happening near us is also very low. So yeah.
That's fascinating. So you're saying historical records
Mm.
that we could see it clearly in the sky,
Yeah,
that everyone just saw this?
there's been writings. If you look for like historical records of supernova observations, you'll find some observations that people have said. At the time, they didn't know what it was, of course. I mean, they must have been
Yeah.
terrified. They
Yes.
didn't know what it was, but based on their descriptions, we know now that it was a supernova. Yeah.
Is it rare for new stars to form, or is that a pretty natural occurrence? I know you said it's declining.
Yeah, in the
I read
modern
that somewhere,
universe,
but
it's declining. So
mhm.
I wouldn't say it's rare. You still see quite a lot of it. I mean, how do I say it? You still see a lot of galaxies with star formation occurring in them. They just all the galaxies then compared to now. They're in like the middle of the history, before very little and then it increases in yeah. So if you look at all the galaxies, you still see star formation happening. Yeah.
And is star formation, is there many ways for a star to form, or is there a most common way for a star to form, or how does that work?
Well, every single star needs a collapse of a gravitation. I'm sorry,
Mhm.
a gravitational collapse of a molecular cloud. So
Okay.
that's pretty.
Okay.
Yeah, every star will form that way. It just depends how big the cloud is. Mm, because the bigger the cloud, if it collapses in a certain way, the bigger the star. You know, and it depends what's in the cloud. It will lead to a certain type of star, depending on the molecules, what the star is going to be fusing and things like that. But they pretty much all start in the same way.
Okay. And I remember your video, one of your videos I watched.
Mhm.
I was trying to keep up the best I could, but I wanted to ask you
Yeah.
because you just brought up spiral galaxies and elliptical
Mhm.
galaxies. I remember in that video you spoke about
Mhm.
bars, and that's something that you were researching at the time when you went on that trip.
Mhm.
I tried to keep up with what it was, but I couldn't quite get it. Could you explain to me what a bar inside of a galaxy is? Or
Yeah. So let's say you have a spiral galaxy, right?
Mhm.
Um, I wish I had a pen. I'd have given you an example. So let's say you have a spiral galaxy. Maybe you can show this for the viewers. In the middle of the galaxy, there'll be a bar, like cutting through the middle of the galaxy, so to speak. It could be in any orientation. Like it doesn't just have to be. It could be this way. It could be that way. It could be this way.
Okay.
How they form is kind of up to debate. But one thing that we know for sure is that they are there. And my
Okay.
research group, I was heavily involved with a group called Galaxy Zoo. They were really heavily investigating what happens in these bars. Like, is there an increase in star formation? Is there a decrease? What happens to the gas content in them? Like, is there normal amounts of gas compared to the rest of the galaxy? These different types of things, So, the yeah, there's not very much known about the effects on the bar of the galaxies, but we know that they form in spiral galaxies. They're less common in other galaxies, a lot less common.
Okay. Is a bar, is it like a string of stars, or is it a string of, is it like, what is it physically?
Yeah, it's physically it will still have the normal galactic stuff, gas, dust, stars, everything like that.
Mhm.
Yeah.
Oh, so is it just like a
It's like a
line
line
of
through the galaxy.
stuff?
Yeah. Line of stuff.
Okay.
It's very weird. Yeah.
And then you mentioned, what was that? The zoo,
Galaxy Zoo.
Galaxy Zoo.
Yeah.
Yes, I had a note about that too.
Mm.
And is that, if I'm correct, like a kind of open, I guess open source. I don't
Yeah.
know how else to put it.
Yeah.
Open source way of researching in a
Yeah,
way,
it's like
or
a
how does that
open
work?
source, community oriented. So what happens is
Mhm.
it's a platform. My PhD supervisor, actually, Brooke Simmons, she's actually quite involved in this. And well, very involved, I should say. She was involved from early on. What essentially happens is, you as a scientist, let's say I'm a scientist, right? And I'm trying to investigate
Mhm.
something about galaxies, and I have 10,000 images. Instead of looking at every single image by myself, I can upload these images to the website and ask viewers to pick out things that they think is interesting or that they think are interesting. So they could pick out spirals, bars, anything like that, and I would aggregate the results, see what they
Mhm.
say, and I have my results there, It's a way for interesting new things to be discovered. It's an interesting way to get an insight into, what people pick out when it comes to certain galaxies and things like that. So yeah, it's a very community oriented open source platform, Volunteers can engage, ask questions from the experts. The experts can get
That's very
feedback on all
cool.
these things, and occasionally a lot of the volunteers will be put on a paper, on a research paper,
Hmm.
because of their discovery. So yeah.
That's very cool. So it could be anyone. You could just go on there and
Any person, as long as you have an internet
wow.
connection from anywhere, it's not restricted. People in Zimbabwe actually have been using Galaxy Zoo.
Oh, that's
Yeah.
good. And how large are these data sets usually?
Oh, it really depends. It could be anywhere from a few dozen sources to a few thousand, and these projects will run for weeks or months. It completely depends on what the
Mhm.
objective. Yeah.
That's very cool. That's a great idea.
Yeah.
But when you're like digging through, I guess not specifically Galaxy Zoo data sets because they're
Mhm.
smaller in a sense
Yeah.
compared to, I'm sure, the other ones you've dealt
Yeah.
with. y- Do you, at what point do you find, or do you use like artificial intelligence to kind of sift
Yeah.
through large data sets to help you out?
Yep. Yes, indeed. I actually did some work for a paper led by Mike Walmsley. He essentially
Mhm.
made a machine learning model called Zubot. So machine learning is a very broad term, but in the way we use
Mhm.
it, it's an algorithm you can train to pick out certain features in something you're looking for. Like for example, classic example is a dog. You give this algorithm a million pictures of a dog. And then you'll
Yep.
say, you give it a new picture it's never been seen before, and you say, is there a dog in the picture? It'll be very good, right? So what I use Zubot for, I kind of like, how you say, what is it called? Um, I increased the training. So I trained it on a new data set of images based on responses from Galaxy Zoo volunteers to help me look for new objects. Fine tuning. Fine tuning is the term where you have an
Mhm.
already trained model and you just add a
Right.
few more images to train it more on different things it hasn't seen before. Yeah.
Yes. I remember the dog. I think I learned that in school
Yeah.
about machine learning, the dog example.
Yeah.
Yes. But I wanted to ask about it because I know in most public conversations, especially now,
Mhm.
um, that most of it's focused on AI, replacing
Mhm.
workers or making things less human or cheating or what have you. It's mostly negative
Mhm. Mhm.
from the public
Yeah.
consensus. But within astrophysics specifically,
Mhm.
is AI viewed as more as a threat or a useful tool or kind of both?
Mhm.
Or how is that going?
So far in astrophysics, it's very much looked at as a useful tool. But again, it depends on
Mhm.
the context. So there's two contexts. If you're actually doing a project using machine learning, where you're trying to train it for images or, um, helping it improve your efficiency in coding or trying to apply it to
Mhm.
things that people already do, very good. People love that actually. There's so many papers and it's encouraged because with new tools comes new efficiency, generally speaking, new
Yes.
improvement in tools. But in general, a lot of people against like using AI to help you write papers,
Of
um,
course.
to write your code, to write research proposals. There, people are more against AI and machine learning. But in general, practical use cases where it can help improve the output of science, generally people are more in favor.
Mhm. Okay, that's interesting. And I know you're still studying your PhD. How is it seen or used within the more of the school side of things? And like you said in papers, 'cause I don't know if you've seen, but the recent, I guess not study, but the statistics from Brown University
Mhm.
in the United States, where I don't know the exact numbers, but a lot of percentage of class was caught using AI to cheat on their tests, and then they were tested again without it, and most people failed.
Yep.
Is that kind of the same? I know PhD research
Yeah.
is a whole different thing than just kind of undergrad
Yeah.
because we're just taking classes
Yeah.
and getting a grade.
Yeah.
Yeah, so how does that differ in
Well,
that sense?
yeah, like when I was in undergrad, ChatGPT just came out in maybe my last 6 months of undergrad,
Yep.
and it was terrible. Like we all tried using it,
Yes.
even the lecturers and everyone was like, "Huh, I wonder how good it is at this physics." It was terrible. Like we just had to learn. In PhD now, like the way it's improved so much, it can pretty much do everything for you. It can do your coding,
Yeah.
writing. I mean, it depends how you use it and depends what you're studying, but I'm pretty sure if you really tried, you could get it to do pretty much a whole paper for you, like from
Yeah.
coding to writing. Claude, all these different types of tools, DeepSeek. Um, but people don't really use it that much because, a lot of work that you do is your own original idea. And it's like a
Yes.
continuation of work you've done in the past. So maybe in 10 years, you'll see people doing their PhDs fully on Claude and ChatGPT. Um, but for people these days who started when it wasn't that good, for us, we still do things manually, the old-fashioned way.
Yes. I mean, I graduated a little late, but being an undergrad when ChatGPT was getting better and where it is now, I feel like I could have almost done all my undergrad
Mhm.
if I wanted to.
Yeah,
If you really utilize it, you could do the entire thing
yeah,
with AI, which is just crazy.
for sure. Yeah, there's no I mean,
Mhm.
that's why you have to do in-person examinations, but then, people can
Yes.
cheat with earpieces and stuff. But
All right.
yeah, in-person examinations really fixes a lot of potential ways of cheating. But it's also
Yes.
tricky, because everyone's going to be using AI in the future,
Right.
So are we going to, until kids are 21, forbid them from using AI, then when they work, they can use it? Or, there has to be a balance that can be struck with such things.
Yes, it's a tough balance because, like you said, it's better to have in person, and maybe we go back to the old ways where this class no technology, you can't
Yeah,
use any
exactly.
technology, you have to study.
Mhm.
But then, are you kind of holding your
Yeah,
students back
from
in a way? So yeah,
technological,
there's
you know.
right advancements, and
Yeah,
that's a good point because I suppose it's not very black and
yeah.
white like mathematics, where there's for the most part one answer. That's interesting. And do you think at some point though that AI could detect something real in
Mm.
space before scientists even understand what it's found?
Well,
And that's a
yeah, I
pretty
think so for
confusing
sure.
question.
I think so. We're even using machine learning right now in huge collaborations and data sets to uh, look for things we don't know. We know there's things
Mhm.
we haven't seen, we don't know yet, we don't understand. So yeah, we're using even me. One of the papers I'm working on is using machine learning to try and understand the behavior of certain objects and certain classes of objects and things like that. I haven't really fully finished with the studies, but there's a lot of promising work that can come from this.
Yeah, for sure. Now, how do you check whether the data that it found is something real rather than just noise or maybe something like that?
Yeah. Well, there's you can just there's a lot of ways you can check. It depends on the data you're looking at. Like let's say
Mhm.
it's looking through a set of images. We'll just check the image, that it hasn't done anything to the image is fine. A lot of times it's just looking for something. There's no potential for it to do anything wrong. We'll just look at the source, investigate, and we're like, oh, okay, it's a crazy source that we've never seen before, or it's normal. That's pretty much it. Yeah.
Hmm. Yeah, I guess.
Yeah.
So it's just testing based on what you already know.
Yeah, exactly.
But for something so large like a black
Mm.
hole and it has so much power and like gravitational pull and it's moving everything around it, why was it so hard for us to find?
That's a good question. Well, first of all, you can't see black holes. Number one.
Mhm.
And if you look in the middle of the galaxy, the closer you get to the center, the more stuff there is obscuring your vision. There's billions of stars, gas
Okay.
and dust which you can't see through. So just based on purely observational attempts, you can't see. So we knew black holes existed for a long time, mathematically speaking. But just because something is mathematical doesn't necessarily mean it will be physical. So you needed
Hmm.
actual tests. And because you can't see a black hole, what do we do? If we know how much it's supposed to weigh, how heavy it is, and the gravitational effects that it has, we will look at the effect it has on other objects around it, which is not something that was very easily done. That's why it won a Nobel Prize. But we do have an image of a black hole. I don't remember, and they use this technique called interferometry. So interferometry is, let's say, a simple case. You have two telescopes separated very far away,
Mhm.
but you use those two combined into one. So you combine the data you get from two telescopes as if it was one telescope. So, but they're both pointed at the object like this, and then the two telescopes observing. But this used multiple telescopes as an interferometer, radio telescopes. So they were, pointed at the appropriate place. The observations were taken, and there's no image, by the way. Yet there's just data. So you clean the data,
Mm.
process the data, combine the data, all these different types of things. You separate the data into multiple groups of researchers because they could be biased. Someone could just be like, oh, there's a black hole, and they make an image that looks like a black hole. You have independent teams
Mhm.
working together. They come together, they have the same image. And that's how after all this strenuous testing that um you have your image. But these things are not easy. These things are, yeah, pretty much only possible in the last 10 years. Yeah.
Mhm. Is that for mostly everything that we kind of take pieces? It's firstly data, and then we create a picture. Like, we don't actually have how many real things of pictures do we have?
Well, we would say they're real because think about it like this, right? Even when you have a camera on the sky, you place it at the
Mhm.
sky. Is no less real than an interferometer, like I just explained. Because what happens is photons hitting the detector and the camera, a CCD, which is creating an electrical signal that will then make the image. It's the same thing, just a more complicated way. A lot of the times you have direct images, like we have direct images all the time. Like if you look at radio observations of the center of the Milky Way, amazing. It's amazing, and these are real images that we have. So yeah, we have them a lot of the time, but we wouldn't say like they're not real.
I got you.
Yeah.
Okay, and I know you said we can't see a black hole. Is this correct in saying that was it Hawking radiation? Is the Hawking radiation the glow around the what is it called? The event
Yeah.
horizon, the black. That's the point of no return. I never understood that because when you get so near to a black hole, doesn't everything like even photons can't escape? So how does radiation sit
Yeah.
on the horizon?
So Hawking radiation is a hypothesis that Stephen Hawking posited, which is that eventually, after enough billions of years, a black hole would eventually essentially disappear. It would be leaking energy. um, how this happens, I don't know. The idea is that the black hole would eventually lose its mass somehow, um, in a radiative manner. But you're right. Once anything passes the event horizon of a black hole, by the way, the glowing thing is called an accretion disk. This is what
Hmm.
is orbiting the black hole. It's accreted, so it's orbiting very fast, so fast and hot that it glows. So that's accretion disk.
Hmm.
The event horizon is just past that. And yes, if anything past the event horizon, nothing should be able to leave. I mean, nothing, even light. Yes, you're right. So that's the event horizon. Around is the accretion disk. Hawking radiation is a different mechanism that he proposed.
That's yeah. And for gravity itself, w- what is it? Like
Mhm,
what is this force? What is it made of? Do we know anything
mhm.
of why gravity acts the way it does?
Well, not to be pedantic, but in a general relativistic model, we don't call gravity a force. Gravity is simply a
Hmm.
property of space time that mass imbues on, so mass causes the curvature of space-time. Why that happens, that's a difficult question to answer. Like that's I think philosophical, like why does mass curve
Hmm.
space-time? You know, or what we do know is that the bigger mass, the bigger effect it has on space-time, which is quite intuitive. The bigger something is, the bigger effect it's going to have. It's simply a property that affects how space-time is, and due to the due to the mass itself, gravity is just a name for how it bends space-time. That's all gravity is. It's a name for, before with Newtonian mechanics. I'm pretty sure in Newtonian gravity, when Isaac Newton was coming up with this, it was a force because it was attraction. So yeah, it's a force. Even technically in day-to-day speech it is, but it's all due to the curvature of space-time. Yeah.
Hmm. So would a massless object, if there is a massless
Mhm.
object, not be affected by gravity?
Well, that's
It's
exactly that's a very important question. People asked why light is affected by gravity, right? Because
I was about
because
it. Yes, I was going to lead to
if
that.
it's two masses attracted to each other and there's one with no mass, what's gonna happen? That's why the understanding of the curvature of space-time is important. Because it's not really those two masses intrinsically that are coming together. If
Hmm.
space is curved, that object, whatever it is, it's gonna fall in, it's gonna go around, whatever it is, because it's a property of what the mass is doing to space rather than what the mass is itself.
Okay,
Yeah.
I understand. Oh, okay, so it just kind of it's not
It's following
getting
a path
affected.
essentially.
Right.
Yeah.
It's going to end up there.
Yes.
So for a black hole,
Mhm.
mhm, and we're moving like at crazy speeds towards one, right? Our entire galaxy.
Not towards one, but we are orbiting one. Like the
Ah,
supermassive black hole's in the center of the galaxy and we're just orbiting around. Yeah.
that's a good point that you bring that because now, in
Yeah.
Interstellar specifically, I remember when they
Oh
get
yeah.
to the black hole, there's planets
Yes,
orbiting.
exactly. Yeah.
Okay, right, that makes more sense. Yes, and then like all the time dilation
Yep.
in Interstellar, when the one guy's on the
Yeah.
ship and then they come
I was
back
like
and he's
decades. He said he waited for
however old.
yeah, very long time.
That's very confusing to me because in the movie, I don't remember exactly how far they
Mhm.
went
Yeah.
to the planet. I don't know if you recall either, but
Yeah.
how is it that every second became I don't know
Yeah.
whatever the
It was
number
a
was.
few
Let's say
days
10
or something
days or
like that, right?
something.
Like
Yeah.
it's because of the gravity. So they were saying like a second on Earth. Let's just use an example with 3 days on this planet. Because this planet
Hmm.
had so much gravity that it was slowing time down relative to Earth. Yeah. It's crazy, right?
That's yes,
Yeah.
absolutely crazy. Who are the what am I trying to say? What practice or do study like black holes the most? I should say.
Oh, like what field in like astrophysics?
What field? Yes, that's the word.
You can have some observational astrophysicists. They're observing what happens around black hole. Theoretical, I'd say maybe theoretical the most because they're really trying to help us understand like what would be happening in these areas. What is it like? What's happening? Is it a singularity? Like, are they're trying to
Mm-hmm.
reconcile general relativity and quantum mechanics and all these different types of things? Yeah, but yeah, you have different types of people working on it.
Dark matter. I know it's a giant buzzword
Yeah.
in the community
Yeah.
and science communication as
Yeah.
a whole, but how much does it actually make up? I hear numbers thrown out everywhere. People are like, "Oh, it's 70%, 30%, 100%."
Yeah.
Or I mean, I've seen 100, but
How much does it make up? Uh, so dark matter is not necessarily a matter by itself. It is essentially we estimate how much matter there is in the universe, right? And
Mhm.
there's a mismatch. What we calculate and what we observe, there's a difference. So that difference is what we call dark matter. In terms of the energy budget, it's not very much. Dark matter energy budget. It's not that much. Dark energy is the one that's really.
Oh, is it dark energy?
Yeah,
Oh,
dark matter is about 30%. Yeah, that's what I remember. Like
okay.
ordinary matter is about 5% of the energy budget of the universe. Dark matter is about 25 to 30%, and dark energy is like 65 to 70%. So dark matter is pretty much all the missing mass that we don't know about. What's in between galaxies and what's inside galaxies, at the edge of galaxies, around galaxies. That's what dark matter is. And we found out that dark matter exists because we were trying to measure how fast galaxies rotate. And galaxies were rotating faster than we'd expect. And the only way you could account for how fast it was rotating is if there's more mass. The more mass, the bigger, the faster the speed. So for decades, even today, people are trying to like, why are our calculations not working? The mass is correct. The estimations of the mass, visible mass, are correct. So yeah, everything is correct, but there's just a huge gap in our understanding that, we estimate that there's 5 times more dark matter than normal matter.
Yeah. Wow. Has there ever been a an equivalent of what, like, if we found out what dark matter was? Obviously, that'd be groundbreaking. Right? Probably win a Nobel Peace Prize or
Yeah,
something.
for sure. Nobel Prize, yeah.
What has there ever been something equivalent to that in science? Like just a giant finding.
I would say that the universe was expanding, When the universe is
Mhm.
expanding, there was a lot of debate, about is the universe static? Is it infinite? Is it expand? Like, I mean, to have been alive at that time as an astronomer would have been a crazy time, I envy them. I hope I hope we find out what this dark matter, dark energy tension is. I mean, it would be a remarkable finding, but yeah, that's probably on that level.
Yeah, I think expanse from the universe is
Mhm.
insane. But what is dark energy then? I mean, obviously you don't know what it is, but
Yeah.
like what
So
in terms of like, yeah.
the universe is expanding, which is kind of fine. With the Big Bang, we don't know when the universe's expansion should slow down. But the universe's expansion is increasing. So every year, let's say, the universe's expansion is getting faster. Where is this energy coming from?
Hmm.
That's what dark energy is. We don't know. The dark is usually used as a prefix to be like, we don't know what it is. So dark energy is like, what on earth is this? We have dark matter, we're kind of being able to investigate. Dark energy, you have no idea at all, you know? And this is what the theoretical physicists will be working on, by the way. The theoretical astrophysicists trying to work up with physical potential explanations of how such things would be possible. Yeah.
So it's just some energy that's been moving us
Yeah,
essentially in
yeah.
a way. Wow. And I know you spoke about this in your video because the expansion of the universe and how it could end
Yeah,
and the different
yeah,
ways it can
yeah.
end. And I know there was the big
Or
crunch was one of them. And what I wanted to ask, is there a way, like, does the universe necessarily have to end? Or is that just a human way of thinking that there's a start and there's a finish?
that's a good question. As far as we understand physics, it has to end somehow, you know? According, I would say our limited understanding, because I agree with you. That's just a
Mhm.
very human, anthropocentric view of things, you know? Um, so yeah, there's physical reasons as to why we think it should end. Like, for example, if the universe expands forever, eventually there'll be such a thin distribution of energy, such an isolation between planets, stars, and galaxies, and there'll be nothing to increase the energy of such things that eventually will dissipate to nothing. And then,
Mm.
like you said, the big crunch where it's like the Big Bang is expanding so much and then it's going to slow down and then it's going to reverse and then collapse. Like all these scales, by the way, on the I mean, time frames of hundreds of billions of years. And we've only, I mean, the universe has only exists for like 13 of that. But I think it's barely more than, what's it called? Speculation. Yeah, it's barely more than speculation, to be honest.
Mm.
Yeah.
Okay. And I wanted to follow up on your video, the big
Mm.
crunch. When you say everything will come back
Yeah.
and close, would that be theoretically? Would it be an instant?
Yeah.
Like it would expand so much and then
No, it
just
wouldn't
like
be an
that?
instant thing. It would be something that happens very slowly. Well, relatively slowly. Like for example, the universe's expansion. We know it's expanding and expanding faster than it was before. Um, but it'll still take many billions and billions of years for that eventually to
Mhm.
happen. Yeah.
Okay.
It wouldn't be an
Yes.
instant thing.
Right. And then the expansion of the universe, is it just, let's say I take, um, I don't know, let's say I take a
Yeah.
bed sheet
Yeah.
and I just keep pulling it, but it doesn't rip.
Yeah.
Let's say
Yeah.
the bed sheet
Yeah.
can't rip for some reason. So I just keep pulling it. Is it doing that or is it adding more bed
Yeah.
sheet? Like adding more
Uh-huh.
stars and expanding like that, or is it just getting stretched?
Well, I heard it explained to me in a very elegant way where I finally didn't have any more questions. It's like not necessarily as if there is a physical fabric of the universe to expand, but everything
Mhm.
in the universe is getting further away from each other, right? It's more like that. For example, they always use this analogy of a balloon. If you put stars in a balloon or dots in a balloon and you blow the balloon up, the stars on the surface will get each further away in distance from each other. It's not a perfect analogy.
And how do astronomers estimate how common like our certain galaxies are without inspecting every single last one? Because I assume we haven't inspected every single thing in our
Of
observable
course, no, we
universe.
haven't. We use the statistics. So let's say we have 1,000 galaxies in a given area, and half of them are red, half of them are blue. And we then measure that again and again and again. We will use that approximation for the whole universe, generally speaking. And you test it at different times. So we look at like current times in the universe, when the universe was just beginning, and then you have different assumptions for different stages in the universe. So mostly it's statistical. We definitely can't look at
Mhm.
every single galaxy. Yeah.
That's how much. So, what? Since it's all based off of statistics, is there ever a 100% like we know, or is there a line where it's like if it's above
Mm.
90, then
Yeah.
we're good?
Well, what we use is something called standard deviation. So, standard
Mhm.
deviation is a statistical measure of how likely you think something will be. So, what we use as a kind of like a gold standard is 5 sigma, where I think the chances are
Mhm.
like 1 in a million. So, if you reach the 5 sigma threshold, I think it's 1 in a million. Let's see, 5 sigma statistical threshold. Yeah, it's something. Uh, oh, it's 1 in 3.5 million. Yeah, 1 in 3.5 million. So if something happens like that, we're like, okay, we're pretty sure that that's the real.
Wow. So it's 1 in 1 million.
Yeah,
That's
1 in 3.5 million.
oh wow.
Yeah,
Oh yeah, 3.5 million.
yeah.
Wow. So is that in a sense like one? There's a 1 in 3.5 million chance that what we see is real, or
No, no, wrong. Like we are so sure.
wrong?
Yeah, it's a
Okay.
1 in 3.5 million chance that is wrong, which means you're pretty certain that it's actually real.
Or in terms of our universe, and I know the Big Bang is kind of like the oldest thing we can see. Am I correct on that? Like the cosmic microwave and
Oh yeah,
stuff
the
like
cosmic
that.
microwave background. Yeah, yeah.
Mm-hmm. What was the significance of that? Because I mean, not knowing anything, I just think, oh, here's the picture. This is really cool. It's super old,
Yeah.
essentially. But what did that actually pioneer in a sense when we found that? Well, how did it change
Mm.
things or change theories or anything like that?
Yeah. So the cosmic microwave background is essentially the afterglow of the universe. You know, the temperature. The I shouldn't say temperature. That's a bit misleading. The wavelengths of light that we see that are left over from the Big Bang. And one of the biggest implications of this, which was found by accident, by the way, the CMB, which we call, for
Hmm.
short, was founded by accident. There was a radio telescope, and there was this buzzing interference wherever they pointed the telescope, and they were like, "Oh, the radio dish, it's faulty, it doesn't work, blah blah blah." But what happened was they actually found the cosmic microwave background by accident. So yeah, the biggest result was that the universe is extremely, extremely homogeneous, which means the same everywhere. From one point in the universe to the other points of the universe, the temperatures are the same, which is not expected because for a universe so huge where information wasn't just darting around, how's the universe so uniform? No, in its temperature, its radiation profile, and all these different types of things. So that led to a new idea of cosmic inflation, where we have the Big Bang, but at the beginning of the universe, the universe expanded at such a rapid rate to be able to
Mhm.
such a uniform temperature in all directions in the universe. Yeah.
That's very fascinating. I mean, I've asked you all of my kind of
Yeah.
what if questions and fascinating questions. Do you have any
Yeah.
yourself that are just kind of like out of reach,
Yeah.
maybe, but
Oh,
like
about
what?
like
Yeah,
astronomy.
yes, or any yes.
That's a good question. The thing is, my questions come with the presumption of God. Like if it'd be like how did God create things the way they are? Like how does the
Hmm.
universe? Because obviously the cop out answer is he can do anything he wants. We can do things too, but we still have a method to how we do them. So
Hmm.
for me, it's like how would something like that happen? Or like yeah, I think that's probably the biggest because sometimes I'll be thinking like how I'm just thinking like existence. Like sometimes I'm just thinking like all of this came from somewhere, somehow, and there's a method to everything, I really believe that there's always a method to something. I don't like the cop out when people say, oh, God did it, which is true, but he always did something with a method, even when it comes to life. We're not just random disordered blobs, everything happens for a reason. A skin color, the way we have opposable thumbs, the teeth we have,
Hmm.
our eyes, how they work, and all these different types of things. Everything has order. So it probably did to do with creation. I'm like, how are things the way they are? Probably the same question people have had since the beginning.
This, yeah, the start of
I think
time.
it's too much
Yep.
of a classic question, like creation. Both life and existence.
Hmm.
Yeah.
Without viewing, let's say, religious
Yeah.
views in this context didn't exist, does physics itself have to say there's a start and then like there was like the laws of physics be like there was something that started this?
Well, that's more of a philosophical question, but I would say so because physics does not exist in a vacuum. It
Hmm.
explains things how they are. So it has to be able to explain certain things, explain how did the universe, how did the Big Bang begin? We know what happens at the beginning, but that's not the same thing as how it started. Those are two different questions. Or like,
Mhm.
how did life begin? These are questions that science should. I mean, a lot of people are working very hard and have been for hundreds of years. So maybe there'll be a scientific understanding as to how that happened. But yeah, there has to be a way, in my opinion. I don't think we'll ever know the
Mhm.
answer, to be honest. Maybe I'm nihilistic in that sense. But yeah, I think we can keep trying. Yeah.
Right. I believe that too. It's gonna be but you said physics doesn't exist in a vacuum.
Yeah.
What does that mean? Because isn't space a vacuum?
Yes, yes, yes. I meant like in the sense that physics as it is in a methodology cannot just say, "Oh, the universe is here, so let's work with what we have." The framework should also be able to explain how it came to be. Otherwise that's another miracle
Hmm.
that's being accepted. And science should be able to explain eventually. It should be. you know. I don't know if the scientific method is enough the way it is, but there's you have to keep trying. Yeah.
Yes. I wanted to ask first, the main question would be, would you choose what you're doing now? I mean, astrophysics, studying astronomy again every single time, knowing everything you know now.
Yeah, I would. you know, I would. It's a very fulfilling subject. It's a subject that
Mhm.
really satiates the hungry mind. For me, I'm someone who's
Yes.
always looking for more knowledge about things, and it's fulfilling in that sense, and also fulfilling in the sense of you tackling questions no one has ever tackled, trying to answer questions that no one has ever answered.
That's
That's
mhm.
also a big thing to be able to do. And I feel like natural
Mhm.
sciences are really what touches at the desire of the human nature. I always use this example that the human nature is explorative. This is why people left their comfortable homes and islands to explore the new world. That's why
Mhm.
people create new tools. That's why people went to the moon. That's how we tried new things like cooking food. Like people look at these things as trivial. We are very, very inquisitive by nature, and that's how we made the world what it is. And I think science is an extension of human nature in that sense. Yeah.
Yeah, absolutely. I mean, I'm so I don't know if I could
Mhm.
think of a better word right now, but like fascinated by people who do take the leap
Yeah.
to pursue a career in science. Because I mean, at least in the United States, you money is very important, whether you want it to be or not.
Yeah.
Unfortunately,
Yeah.
right? And unfortunately,
Yeah.
again, a lot of science and research, unless you go to an industry or private, you might not make as much as if you did another
Mhm.
career. Being how smart you are.
Yeah, it's true.
And I think it's just so fascinating that people have this passion, and it's you're exploring a new
Mhm.
frontier essentially. Like you're taking on what we did thousands of years ago by going on a unknown ocean
Yes.
and being like, what? Well, I don't know what's over there, but I'm gonna find out.
Yeah.
And so that's very very cool
Yeah.
to me. But and I know it's extremely difficult.
Yeah.
Obviously, there's been moments that are extremely difficult. So what do you say to a person that's maybe a
Mhm.
student, a college student, maybe going to
Mhm.
college, and they're juggling, maybe I want to pursue something in astronomy, astrophysics, whether it might be that, but like, what has made the most difficult parts of everything worth it to you?
That's a good question. I think you have to really want what you're doing. Whether you're a biologist, a literature major, whatever it is, you have to really want to do what you're doing. And you have to think, could I suffer for this? Because things get difficult. You can't understand the concept. Your grade is gonna determine your future and all these things. Can you really
Mhm.
withstand the difficulties that come through? And if you feel like, there's something where you wouldn't be able to do that for, that's fine. But, I was willing to suffer for astrophysics. you know,
Mhm.
I don't know if I could do that for every subject. So yeah, that's something important.
Yes, and something you said in one of your videos really stuck with me. You said, I think it was on that trip you were to the telescope. You were not having great sleep, obviously, and then one of your
Yeah.
colleagues, who the only one who could drive, or the only two people who could drive left, so you had to walk up the kind of the peak
Yep.
every day, and you were very tired. But then, and then it was your first day, I think, running the telescope, if
Yeah,
I'm
yeah,
saying
that
that
could be. Yeah, yeah,
correctly. Yeah,
operating
functioning
the
it,
telescope. Yeah,
operating, yes. And you said it's gonna be a lot of pressure, but you said pressure is a
yep,
privilege.
it's
And that's amazing. Like that stuck with me right away because it
yeah,
is. It
yep,
really is. It's a privilege to be in that space and have the pressure to do what you're
perform, yeah,
doing. But dealing with all that pressure, like you said, where a letter
mm,
defines your next
yeah,
step in your career, it's like very, very black
yeah,
and white. If you don't do well in this, you're gonna end up
yeah,
somewhere else. How have you dealt with that pressure? Even though you
yeah,
love the topic so much, like if a student
yeah,
was
yeah,
struggling with tests and everything, but they love it
yeah.
so much, what do you say to them?
You know, the way I look at things when I have no choices, I just have to do it, you know? You know, I just don't have a choice. And not everyone necessarily has the same upbringing. I remember,
Mhm.
my I look back on this in a funny way, by the way. Like my parents would be like, if you don't do well at school, you're gonna be homeless. I'm like, I was a kid.
That's what my parents
I
yeah.
was so scared. So even when I was 20,
Mhm.
21, sometimes even now, I'm like, hey, I have to succeed. And you don't necessarily need that pressure
Yes.
from the outside, but even from within yourself, you have to succeed. If you really, you have to take up every opportunity as it comes. And it's a little sacrifice for a lot in the future. Once you have tenure,
Yeah.
it'll all have been worth it. So yeah.
Yes. And how do you deal with, because you've done so well for
Mm,
yourself and you knew there was gonna be
mm,
pressure and times of hardship and difficult parts, but how have you stopped and, the phrase smelled the
mm,
roses? Because you reach a peak. And at least for a lot of people I know, and me personally too, a lot of times, I'm like, okay, I need to practice, 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 and get into the
yeah.
school. Got into the school, and then I'm like, okay, but now I need to
Yeah.
practice, 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 and get honors or whatever, and practice, practice, get this job. But then I get the job, and then you want more, but you're not like, whoa, look what I've all done. How do you kind of smell the
That's
roses?
that's a good question. I mean, I kind of fell into that issue in undergrad. The only time I really relaxed was probably my last month, my last month of my degree. But a lot of the times for me, I mean, whichever terminology you use, for me, I think about what I prayed for, or some people what they wished for. And you have to think you're living that right now.
Mhm.
You'd be praying, you'd be really desiring, the situation you're in now. So sometimes you have to take some time to be thankful, appreciative, and work hard, but also acknowledge the situation you put yourself in.
Mhm.
Yes.
Yes, for sure. And was there a moment that I know we talked about
Yeah.
this earlier, like you're kind of like, ooh, big astrophysics moment, but was there a moment where you were like, look what I've
Yeah.
done. This is amazing.
Yeah.
And just paused for a minute. Not to be like
Yeah. No,
bragging or
yeah.
anything, but just with internally being like, I did it.
Probably when I presented at my first international conference. My first conference that I presented was in South Africa 2 years ago in the summer. So that was very fun. Yeah, that was a good experience to be like, okay, I'm around people who are, like an inspiration to me, in an astrophysics
Right.
context. So being able to be around those people and networking and getting opportunities and stuff like that, I was like, okay, I have a foot in the door, so to speak.
Yeah. Well, that's awesome. And how do you deal with the pressure of presenting? I know that's kind of an off
Yeah.
topic question, but just in general, presenting.
To be honest,
Or do you get anxiety or do you get excited or is it just,
I don't really feel the pressure, to be honest. Like, not like in a bragging way,
mm,
but I don't really feel
all
pressure
right.
to, like, when I present my talks. Um, I feel like I'm just presenting to friends. That's how I view it. 'Cause no
Mm-hmm.
one no one's really out to get you. When like when you present your research, no one's gonna be like, "Oh, he made a mistake, or he did this or this." Like, people, you might have the odd person who's like that, but most people are very friendly.
That's a good point. I feel like for the most part, in any career, when you're presenting, most people aren't going to be like, "Oh, you didn't." Yeah,
Exactly.
that's a good point.
Yeah.
And then this is more of like the person I read on your website that you have like personal hobbies like jiu-jitsu.
Yeah.
That's one of them. You said that earlier. Remember you started, was it when you were at Oxford? Or
I did actually no, I started before, just before I was in Oxford actually. Yeah. Yeah, I did jiu-jitsu, I did wrestling. I did a lot of things for hobbies: swimming, horse riding, tennis, track, like athletics.
you did Muay Thai too. Yeah, I remember you
Yeah, I
mentioned
did
that.
a few
Is that right?
classes.
Is that correct?
But these days I'm more chill because I'm writing my thesis. So all I do is I started going back to the gym lately. I mean, I was out of the gym for a while. I was like sick for a few months, but all is good. So I just
That's good.
yeah, I started going to the gym again, church. That's pretty much it. Like church,
That's good
gym,
though.
home, and work.
Yeah,
Yeah.
I mean, you're pretty busy. But yeah, I always wanted to, that caught my eye because I always wanted to try getting into jiu-jitsu or any martial art in a sense.
Well,
And I was just wondering your thoughts on it.
I,
What do you
I I'd recommend wrestling instead of jiu-jitsu. Every person I
really?
see in jiu-jitsu, including myself, their elbows are messed up, their wrists, their knees, their shoulders, their ankle.
Yes.
Like I've dislocated each of my knees. Like my right knee, I think was one time. My left knee was twice. Like I still have knee issues. I always have to be in the gym to keep my legs strong. So
Mhm.
wrestling is better. Wrestling, you don't because jujitsu like locks your joints and like there's a lot of torsion on your joints, like they're locked all the time. So
Mhm.
wrestling is just you have to have strong legs, but your knees will be fine.
Yeah, because I was wondering. I just wanted to do something maybe
Yeah.
recreationally, but I heard of the joint damage that kind of cures over time. But I wanted to something that would challenge my mind to get better and learn techniques without too much damage,
Yeah, you should
I
try
suppose.
climbing. I climbed for that reason. Yeah,
Yes, I love
bouldering
climbing. Yeah.
because the thing is
Mhm.
no one fights recreationally unless you're very old, Like if you want to fight recreationally, you're not gonna enjoy it because everyone is out to get you,
Oh,
I noticed that it's very intense. It's something I'd only do if I had the time to do it properly.
yes. Okay, that's a good
Yeah.
point. Yeah, and I also wanted like not so much a competitiveness,
Yeah.
but a drive towards
Yeah.
something like you can win. You can win or
Yeah, I like
lose.
that. Yeah. I only
Because,
had one competition, but I like competing.
oh yeah, how did that
It was
go?
good. I was second place. First competition. I'd been training for a few months, so oh
Oh
yeah.
wow. Was training in jujitsu or working on completing your PhD harder?
Uh, jiu-jitsu.
Really? Really?
Yeah, I mean, it's not PhD. The thing is, it's not that difficult. It just is time consuming. You just have to be very
Time consuming.
disciplined. But in terms of
Hmm.
difficulty, it's not that bad. It was easy. Undergrad was the hardest thing I've ever done. My undergraduate degree.
Go. But yeah, I guess I'll just wrap it a bit. I really appreciate you coming on. I felt like I was a kid just raising my hand to the teacher the whole time, and it was
No,
amazing.
no
Like I
worries.
couldn't
It's
ask for
okay.
anything
I'm
more.
glad. Happy to be here. Yeah.
Yeah, but it was a pleasure. Thanks so much
Yeah.
for coming
Thank
on.
you too. I'm glad.